Motivated by the eclipse next week, we are, Jeff, Brian, and I are going to be talking about solar eclipses in general in Wolfram language. So this is a summary of the talk. In the first part of the talk, I will discuss the astrofunctionality in Wolfram language. Then we will talk about the main function we use to compute about solar eclipses. And then I will mention briefly the technique that is used behind those computations. And then Jeff will talk about the eclipse next week. He will compare it to the eclipse in 2017, and he will talk about other interesting things related to the eclipse that day. Okay, so let's start. So since late 2022, Wolfram language has a very powerful functionality to compute astro data and related results like maps of the sky. So the main function we use is called astroposition, which is a function that uses internally the most precise and recent data provided by NASA, this data, to compute positions of everything in the sky. So this is a function that computes, for example, the position of the sun, and we see how we can do it in real time. Then we can change to other coordinates. For example, this was the position of the sun in horizontal coordinates, azimuth and altitude. This is the position of the moon right now in equatorial coordinates, so right ascension and declinations. And we can also see how it changes. So we saw before how fast this was changing, mostly due to the rotation of the Earth. This changes much more slowly. And this is the actual motion of the moon around the Earth. So here we have the second function that we use in the astrofunctionality, which is astrographics. This is the function responsible for producing maps of the sky. And so what we are asking here is to have a map around the star Betelgeuse in equatorial coordinates again. So this will be right ascension and this is declination in degrees. And we are going to have an astro range of 25 degrees. So that means that essentially from the center to the border of the sky, we have 25 degrees. And that's a map. We can add other things like nice illustrations for the constellations, the 88 constellations in the sky. So this is the same thing with the same coordinates and range, but now we add this other background option, specifying that we want this type of background with constellations. Or, for example, we can ask for a map of a different area of the sky. And so here we say, well, plot a point in white at these coordinates, so the 0, 0 of the galactic coordinate system. Again, 25 degrees of sky. Now we are using galactic coordinates. So this is galactic longitude and this is galactic latitude, in which the galaxy, of course, looks flat, oriented horizontally. We have this background, which is this nice image of the galaxy, and we are adding grid lines. Perhaps you don't see it via the zoom, but we do have a grid of galaxies, of lines in galactic coordinates, and you see how the 0 latitude corresponds to this axis, which is aligned with the plane of the galaxy. So there are many other reference frames. There are many other options that you can use in astrographics to have a very detailed and nicely represented map of the sky. Now, what is the main function to describe solar eclipses? So it's called solar eclipse, and by default, it reports the date of the maximum eclipse of the next eclipse, which is, of course, the eclipse next Monday. And this is computing the date, the exact moment, the exact second of the maximum eclipse, which is the moment in which the axis of the shadow produced by the moon gets closest to the center of the Earth. For example, we can now do again an astrographics. Now we are centering at the sun. We have the reference frame being equatorial, and we specify that we want to look at that position at that instant. And so we move hours from -1 hour to 3 hours later after this instant. And this is what we see. So we see the moon coming here. This is computed from here, from Champagne, and from Champagne we will not see totality. You see, we will have almost totality, but not quite. So this is enough to still require the use of glasses to look at the sun. Or we can now use ecliptic coordinates and look at the Earth from the sun. And now what we see is that we see here the moon passing in front of the Earth as seen from the sun. So this we understand from this map why is it that we will see the eclipse only in the north hemisphere. Okay, so with these computations, you see how astrographics and astroposition can compute everything related to the eclipse. So something else we need is very nice control on the position and the moon of the moon. So we have the new function in Wolfram language 14, new moon, which reports the instant of the next new moon. Interestingly, we can change this date, which you see it's number is the 8 in April, to a lunisolar calendar. For example, the Hindu or the Jewish calendar. The Jewish calendar is a lunisolar calendar, and in those calendars are aligned with new moons, and so it will happen that new moons always happen in the very last or initial days of months, and full moons will happen in the middle of the month, right? So that's the date of the next full moon, so about 2 weeks after the eclipse. We have a function called the lunation number that counts new moons from the first one in year 2000. And again, we can have it dynamic, and we see how it's changing continuously and how this number is progressing. So the eclipse that we will see on this date near this new moon will happen to be the new moon number 300 after the beginning of the year 2000. So here we have all new moons of this year, 2024. And if we see what happens for each one, for example, the next, if we go to the first one in January, we see how the moon travel far from the moon. However, if we go to the one next week, we see how the moon is going to pass in front of the sun, right? As seen from somewhere on Earth. Okay, so yeah, so that explains why for most new moons we don't have a solar eclipse, because the moon passes a few degrees from the sun, but twice a year, from 2 to 5 times a year, the moon will pass close enough that from somewhere on Earth a solar eclipse will be visible. Okay, so the function that we have rewritten for version 14 to compute solar eclipses is called SolarEclipse. This function has access to the full range of dates provided by NASA, which is from year minus 13,200 to year plus 17,200. So more than 30,000 years. In that range of years, there are more than 72,000 solar eclipses, and Wolfram language gives you access to all of them, all properties, about 100 properties, and including polygons, dates, very precise, etc. You can compute global properties and also local properties if you specify an observation date or observation instant. So this looks a bit small, but it's important to know terminology. So that's the sun. Of course, this is not to scale. That's the moon passing in front of the Earth. And we see how there is a cone here of shadow that's called the umbra. And there is this vertex of the cone, and the other side is called the antumbra. And then there is this other cone with vertex here, which is the penumbra. So all those areas of the Earth in which the umbra hits will see totality, parts, or annularity if the place of the Earth is in the antumbra, and then the areas of the Earth in the penumbra will see a partial eclipse. So this is up to scale. That's the sun with a radius of about 0.7 million kilometers. So that's the orbit of the moon, that little circle, and the Earth is there in the middle. If we enlarge this by 400, then that's the moon, that's the orbit. So this circle we see here is that little circle, and now we can see the Earth. So you see how interesting it is that when we enlarge by 400, the sun and the moon look nearly identical in size. So that coincidence, that's amazing coincidence, is what allows us to have both annular and total eclipses, and even a mixture of them sometimes, hybrid eclipses, as we will see in a moment. So let's discuss first global properties. So these properties are properties of the eclipse as a whole, not depending on a location on Earth. So again, let's compute the next eclipse. That's the maximum eclipse. We identify in Wolfram language eclipses by their maximum date. And so, for example, we can say, what's the type? And it's going to report total. So the next eclipse is of total type. We can also do the computation for some other date. For example, what's the next eclipse after the beginning of the year 1900? And we get that date. We can also say, okay, look for the next eclipse in the opposite direction. So what's the previous eclipse before 1900? And we get that date. We can also search by type. So for example, what's the next eclipse from now of type total? Of course, it's going to be the next week. But what's the next annular eclipse from now? So that's going to happen later this year, right? As I said, every year there are 2 to 5 total eclipses. So that's another eclipse this year. So if we look for the next hybrid eclipse, we will find it in year 31. And if we look for the next partial eclipse, so it will be in year 25. So a nice property we have in SolarEclipse is a map. If you don't specify a date, it will mean the map of the next eclipse, which is this map. But this shows the path of totality, some level lines for the different magnitudes of the eclipse. So this is where the eclipse starts at sunrise. This is where the eclipse ends at sunset. Yes, as I said, the default property we report is what is called the maximum eclipse, which is when the shadow axis passes closest to Earth's center, right? So you can explicitly ask for that property. And there are many other properties. For example, you can ask where is going to be the best place to observe the eclipse. So where is this going to be this maximum? And we get that position. This is a manipulate just to explain what happens during the eclipse. So here we see the moon traversing in a straight line in front of the Earth as seen from the sun. And we see how the combination of this motion together with the rotation of the Earth produces this curved totality path. This point here in orange is the maximum eclipse. It's the moment in which the axis, which is this little circle, actually this is the umbra, so this is the penumbra, this is the umbra. When it passes closest to the center of the Earth, that is the maximum eclipse, which this time will be in Mexico. Okay, and then the eclipse proceeds and it ends there. So that was an example of a total eclipse. Now, what happens in an annular eclipse? Well, we can go to the annular eclipse in 2030. We get this type of map. And now what we will see is that this is a similar situation as we had before. But now look at how the penumbra traverses the Earth. And the thing is that when it reaches the center, you see how the moon is far enough that it cannot cover fully the sun. And so we see an annular eclipse. We still see the sun. And in these situations, we typically need glasses. We can have hybrid eclipses. For example, this was a hybrid eclipse in the year 48. And the geometry can be similar to that of an annular or to a total eclipse. But the thing is that when the eclipse starts, we see a little bit of the sun. So it's annular. Then as the eclipse proceeds, and we are here in the middle, now the moon covers fully the sun, so we are in totality. And then at the end, it may happen, and it did happen in this case, that we see an annulus again, right? So hybrid here means it's annular near the beginning and the end, and total at the center of the eclipse, right? Okay. And then a partial eclipse. A partial eclipse is simply one in which the central part, the umbra, does not touch the Earth. And so nowhere from the Earth we can see totality. And so, for example, if we look at the sun from a place like here, it almost covers the sun, but because the umbra doesn't touch that point, we don't see. And so when that happens, we have this type of situation on Earth in which the two lobes that we were seeing before gets merged. And so the maximum is here. This place is exactly that place over there. Okay. Something else very interesting for eclipses is cycles. And so this is known from the times of the Greeks. And so each eclipse belongs to a family. It's called a Saros series. For next eclipse is going to be series 139. It has, and the interesting thing for the series is that eclipses are periodic. They are all like 19 years from each other. That's called a Saros. And it's exactly that difference from one to another. You see with very precise error. And so the magnitudes of a family typically are small, then they reach one. So there are total and annular eclipses and hybrid eclipses here, and then they go down. And if we plot this, we see how the eclipses, this is evolving during the series. This is the totality paths, and they look kind of related to each other, right? And so it is just a problem of geometry of the orbits of the sun and the moon. And then very quickly, I will also mention that all eclipses also belong to another cycle called the inex. So there is the Saros inex property, giving you both numbers, the Saros numbers, the inex number. And so every eclipse can be placed in this table, which can extend to both sides a lot. And each eclipse is a number, and it belongs to a family. So one of these vertical families is the Saros, right? And this is 139 Saros for this eclipse. This is an inex family. This is a Saros family. So each eclipse is a point on this diagram. It's a very interesting classification with lots of information. Local circumstances. So how do you compute local circumstances, local properties? So you have to specify where you are observing or when you are observing. For example, if I observe from Champagne, when is the next eclipse going to have a maximum? So that will give me the second, right? So this doesn't mean it's totality. It's just the best moment to watch the eclipse. If you want to specify some other date, you can ask for another property like local magnitude, which means what's the fraction of the diameter of the sun covered by the moon? You can ask for contact dates. You can, for example, plot how the magnitude evolves with time, right? So this is the maximum. This is 1 hour and a half or so before the eclipse. It goes up and it goes down again. It doesn't reach 1 because we don't have totality here. And for example, you can get polygons of where is the shadow. And here we are in Urbana-Champaign. And so these are the shadow of the moon as it progresses minute by minute. And yes, I will finish saying that the key concept, the key technique used to do these computations was introduced by Bessel in 1829. And it's still used. It's very powerful. And it consists in creating a reference frame. This is the Earth, exaggerated, of course, to exaggerate the obliqueness of the ellipsoid of the Earth. And with this, we can, right, we have here the shadow of the moon. We can change the position of the sun. This is what the shadow does during an eclipse, is moving, etc., etc. And so once we have this reference frame, it's easier to compute all properties that relate to the eclipse for the Earth. You give a position in these coordinates, and there are special techniques to do every computation you want. That's a reference frame that moves as the moon passes in front of the Earth. You see how this frame is going to be moving just to always align, to make perpendicular the shadow of the axis of the shadow with respect to the reference frame, to the Besselian reference frame. And yeah, so here I leave as an exercise for those of you downloading the notebook, how to compute one of the properties, namely the moment of maximum eclipse, right? So this is just the Besselian element functions, of course, reported by the SolarEclipse function. And then we get these functions as a function of time. This is time in hours from the maximum. And then what we do is X and Y are just the coordinates in that plot in the Besselian frame. So if we compute the minimum of the distance from the position of the shadow axis to the center of the Earth, which is this thing, we will find the moment of the maximum eclipse. We just convert it into hours, and we get that number, which is exactly what SolarEclipse would report, you see, to milliseconds. So this, once you have these functions, you can compute anything you want about the eclipse. Thank you.